Hello dear student, this is my lecture number 3 and the topic dimension of a vector space. In this video, we are going to see three important theorems based on dimension of a vector space. Let us see first theorem. Let phi be a vector space with dimension of phi equal to n if set S containing vectors v1, v2, etc. vt is linearly independent set with t strictly less than n, means number of vectors in S is less than dimension of p, then S can be enlarged to a basis for phi. That is, there are vectors say vt plus 1, vt plus 2, etc. vn such that the set containing vectors v1, v2, etc. vt, vt plus 1, vt plus 2, etc. vn is a basis for phi. Let's prove this. Let phi be a vector space with dimension phi equal to n. So as dimension of phi equal to n, every basis of phi has exactly n number of elements. Suppose that S containing vectors v1, v2, etc. vt is linearly independent set with t is strictly less than n, means number of vectors in S is less than dimension of vector space. Let phi be an arbitrary vector in vector space capital Phi. Consider the set S dash, which is obtained from the set S by joining this vector phi. So S dash having the vectors v1, v2, etc. vt, phi. Here S dash is linearly independent, because if S dash is linearly dependent, then there exist scalars not all 0, such that the linear combination k1 v1 plus k2 v2 plus etc. k3 vt plus kv equal to 0. Now again here k is equal to 0, because if k is not equal to 0, we can rewrite this equation as phi equal to minus of k1 upon k times v1 plus minus of k2 times, minus k2 upon k times v2 plus etc. minus kt upon k times vt, means phi is linear combination of v1, v2, etc. vt. As phi is arbitrary vector in vector space V and is linear combination of vectors in S. Therefore, we can say that set S spans V. Now here S is linearly independent and S spans V, and therefore S is the basis for V. But S has number of elements less than n, so which is not possible, as dimension of p equal to n and S has t number of elements with p strictly less than n, and therefore your set S dash must be linearly independent. If the number of vectors in S dash, how many vectors in S dash are there? T plus 1. So if this T plus 1 equal to n, then S dash is a set with n linearly independent vectors in Phi, and therefore S dash is the basis for vector space Phi. Now if these two are not same, that is t plus 2 is t plus 1 is strictly less than, here I have forgot t. So if t plus 1 strictly less than n, then processing as before with S dash. So we can obtain a linearly independent set, say S double dash, with how many elements? T plus 2 elements. Again, check whether this t plus 2 equal to n. So if t plus 2 equal to n, then set S double dash will be a basis for Phi. Now continuing in this way, since n is finite, we can obtain the vectors vt plus 1, vt plus 2, etc. vn, such that the set B containing the vectors v1, v2, etc. vt, vt plus 1, etc. vn is linearly independent set with n vectors. And as dimension of V equal to n, B is a basis of vector space V. And thus, we have proved that any set, any linearly independent set can be enlarged to a basis for vector space V. So remember this result. Let's move toward next theorem. If W is a subspace of V, then dimension of subspace is less equal dimension of vector space, and moreover, dimension of W is equal to dimension of V if and only if W is same as vector space V. Let's prove this. Suppose that V is a vector space with dimension of V equal to n, means every basis of V has exactly n vectors. Let W be a subspace for vector space V. Let us consider the basis for W. So let B containing the vectors V1, V2, etc. Vt be a basis for V. Now as B has how many vectors? 1, 2 up to P. So total P vectors, and therefore dimension of W equal to P. Now as W is contained in V and B is linearly independent set in W, we can say that B is also linearly independent set in V. Now by previous result, we can say that B can be enlarged to a basis for V. So let B dash containing the vectors V1, V2, etc. Vt plus 1 Vn, and which is a basis for vector space V, and therefore dimension of V equal to n. Dimension of W is T and dimension of V is n. So we can have T is less equal n. That is dimension of W is less equal dimension of V. Moreover, if dimension of W equal to dimension of V, then any linearly independent set with n vectors in V is a basis for W also, because these two dimensions are same, and therefore you can say that W is nothing but a vector space V. And conversely, if W is V, then any basis for V is also a basis for W, means dimension of W is equal to dimension of V. So again, you have to remember this result. Dimension of a W space, dimension of a subspace is always less than or equal to dimension of a vector space. Let's see next important result. Let V be a finite dimensional vector space. Then following statements are equivalent. Statement number 1, B is given as a set containing vectors U1, U2, etc. Un. B is the basis for V. Statement number 2, B again containing same vector is maximal linearly independent set in V. And third statement, B is minimal generating set. Now we have to show that these three statements are equivalent, means if either one of these three statements is true, then rest of two are also true. So to show that these statements are equivalent, we show that statement 1 implies 2, 2 implies 3, and then 3 implies 1. So we assume that V is a finite dimensional vector space, and suppose that dimension of V equal to n. Now we prove that 1 implies 2. So assume 1 and prove that 2 holds. So suppose that B containing vectors U1, U2, etc. Un is a basis for vector space V. We prove that B is maximal linearly independent set in V. Yes. For that, let us consider B dash containing vectors more than vectors in B. So B dash containing vectors U1, U2, etc. Un plus 1 etc. un. Therefore, we observe that B is contained in B dash. Now, since dimension of P equal to n, any set containing more than n vectors is linearly dependent. Now, this B dash set containing vectors more than dimension of P, therefore B dash is linearly dependent set in P. And thus, B is maximal linearly independent set in Phi. Means no any other set containing more than vectors in B is linearly independent. So B is maximal linearly independent set. Now we prove that 2 implies 3. So assume 2 holds. Let us suppose that B is maximal linearly independent set in Phi. We prove that D is minimal generating set. That is to show that no proper subset of B that generates Phi. So we take a proper subset of B as S and containing vectors u2, u3, etc. un, and therefore S is proper subset of B. If you want, you can write here. S is a proper subset of B. If possible, suppose S generates Phi. So let's see what happens. S generates Phi. So every vector in Phi can be expressed as linear combination of vectors in S. Now, as u1 is the vector in Phi and it is also a linear combination of vectors in S, and therefore there exist scalars k2, k3, etc. kn such that u1 equal to k2u2 plus k3u3 plus etc. kn un equal to 0. So this equation we can rewrite this as minus 1 times u1 plus k2u2 plus k3u3 plus etc. kn un equal to 0. Now this is the linear combination of u1, u2, u3, etc. un, and with scalars not all 0. So this minus 1 which is k1 and this is not all 0. So implies u1, u2, etc. un is linearly dependent, which is not possible since these vectors are linearly independent, and therefore S cannot generate Phi. Means no proper subset of B generates Phi, and this means that B is minimal generating set. Now third, 3 implies 1. So we assume statement 3 holds and we prove that statement 1 holds. So suppose that B containing vectors u1, u2, etc. un is minimal generating set. We prove that B is a basis for Phi. Now as B is a generating set, so it remains to show that B is linearly independent set in Phi. So let's prove this result by contradiction. So if possible, suppose that B is linearly dependent set in Phi, and therefore there exist scalars not all 0 such that k1u1 plus k2u2 plus etc. kn un equal to 0. So as all scalars are not 0, so without loss of generality, suppose k1 is not equal to 0. So from this equation we have k1u1 is minus of k2u2 plus minus of k3u3 plus etc. minus of kn un. So as k1 is not equal to 0, we can divide throughout by k1. So we must have u1 is equal to minus of k2 upon k1 times u2 plus minus of k3 upon k1 times u3 etc. minus of kn upon k1 times un. This means that u1 is a linear combination of the vectors u2, u3, etc. un, and therefore you can say that The set containing vectors u2, u3, etc. un generates phi, and obviously this is a proper subset of set B. So here we have proved that proper subset of B generates V, and which is not possible because our assumption is that B is minimal generating set, means no proper subset of B generates V, and therefore B must be linearly independent set in phi. Now B is linearly independent set and B contains exactly n vectors. N is the dimension of phi, and therefore B is a basis for vector space phi. So this result we have proved here. So this is again important result on dimension of a vector space. One more remark I want to tell you is that if W1 and W2 are subspaces of a vector space phi, then we said W1 plus W2 defined as the set containing elements of the type W1 plus W2, such that this W1 is from the set W1 and this element W2 is from the set W2. Then it is a subspace of phi. So you can verify three conditions for a subspace. So show that this set is non-empty, show that this is closed under addition and closed under scalar multiplication. If these three conditions hold, you conclude that the set W1 plus W2 is a subspace for a vector space phi. And if this happens, then we can verify that dimension of W1 plus W2 is equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. So this is our lecture number 3 on the topic dimension of a vector space. Next, we will see examples based on to find dimension of a subspace of a vector space. Let us stop.